Hello and welcome to the NIJ Forensic Science Research and Development webinar series. Today we will first hear from Dr. Catherine Weissensee, Professor and Chair in the Department of Sociology, Anthropology, and Criminal Justice at Clemson University, on improving postmortem interval estimates, mass collaboration, and machine learning in the service of forensic science. Then we will hear from Dr. Angela L. Harden, Research Assistant Professor with the Injury Biomechanics Research Center at The Ohio State University, on the Forensic Anthropology Skeletal Trauma, or FAST, database. Without further delay, I will turn things over to Dr. Weissensee.
Hello, and welcome to this section of the webinar. I'll tell you about a project focused on improving PMI estimates using mass collaboration and machine learning models. I'm excited to be here to talk about the progress of this research. This project is part of a 3-year grant funded by the National Institute of Justice. I want to quickly acknowledge the interdisciplinary team of researchers who work on this project. As you see, we have a team of anthropologists, geospatial scientists, and data scientists working together to address the problem of time since death estimations. Today, I'll introduce GeoFOR, a mass collaborative application that we have created that can provide a PMI estimation from a large reference data set. Then we'll go over how to submit cases in the GeoFOR database. And finally, we'll discuss the machine learning models used to generate PMI estimations and the Bayesian approach used to model the decomposition process. PMI is often one of the first questions investigators want to know when remains are found. And given the current methods available, it's generally what I feel least comfortable providing. Methods for estimating age, sex, population affinity, and stature were developed and tested on large reference data sets, like the Forensic Databank. This data is drawn from forensically and geographically representative cases. It's the model of the Forensic Databank and the power of mass collaboration to address questions important to the forensic community that was the impetus for GeoFOR. GeoFOR is a mass collaborative forensic taphonomy database that uses ArcGIS and machine learning to provide free and accessible data-driven PMI estimations to registered practitioners. As you'll see, using this large geographically diverse reference set, we're able to estimate time since death with known error rates in ways that aren't possible in the absence of training data. We're also able to inform research design related to decomposition based on the observations in the GeoFOR dataset. We know that decomposition is a process impacted by many variables, and it would be nearly impossible for any one person or place to provide the necessary data to make robust predictions and provide a meaningful understanding of the decomposition process. PMI estimation is an area that frustrates many practitioners, so mass collaborations allow us to work together and improve the methods available. Mass collaborations work best and achieve a meaningful scale when they capture work that's already happening. The work of observing decomposition characteristics is happening every day in medical, legal, and research facilities. Mass collaboration facilitates collective problem solving and allows us to tackle the complex problem of PMI estimation together. At the end of the project, and in support of open science initiatives, the dataset will be made available to researchers so that we can continue to improve methods for determining PMI and increase the likelihood of identifying people. So how does mass collaboration work using GeoFOR? Collaborators request access on the GeoFOR website, and once approved, you'll receive a unique username and temporary password. The case submission process was designed to be quick and straightforward, with checkboxes and pull-down menus available to minimize input errors and facilitate accurate data collection. It has flexible formatting where the data could be input on your phone, tablet, or desktop. Using the location information submitted by the collaborator, GeoFOR is able to integrate pre-existing weather and environmental data into the model. This graphic provides a visual representation of the process as the user requests access and submits information to GeoFOR. The data is stored in individual accounts, and the weather data is automatically pulled from nearby weather stations. The machine learning model uses the case information and weather data to provide an estimate of PMI, which is emailed to the user. Here's a closer look at the GeoFOR survey itself. The first page includes information about the date and location of discovery. Step 2 includes anonymized information pertinent to PMI estimations, including sex, a general age category, body size, and deposition site type. Step 3 involves selecting the characteristics of decomposition observed on the individual at the time of discovery. I want to stop here for a minute and talk about the characteristics of decomposition. In the initial iterations of the survey, the remains would be classified as stages, such as fresh, advanced, or skeletonized. However, I had trouble identifying uniform definitions and characteristics that make up each stage in the existing published literature. The notion of classifying decomposition into stages has frequently been used, and it was where I started when I began to think about how to collect standardized information about decomposition. But then I began to question how reproducible stage information is. Do individuals always move through the stages of decomposition in uniform ways, regardless of environmental factors? Existing stages don't account for the nuance as an individual passes from one stage to the next. I thought perhaps it would make more sense to begin with the individual variables commonly associated with the stages of decomposition, so that these fundamental questions related to stage definitions could be examined. This is a long way around of saying that all of the characteristics observed in the remains are recorded in the survey, as opposed to stages, which has enhanced our ability to model PMI and decomposition in interesting ways. For example, you might observe greening of the abdomen, skin slippage, discoloration, marbling, bloat, and purge on an individual. GeoFOR allows you to capture all of this information, rather than collapsing it into existing stages of decomposition. After selecting all characteristics of decomposition observed on the body, users progress to Step 4, where insect and vertebrate activity is recorded. In Step 5, users can choose to receive a PMI estimation solely through GeoFOR's machine learning model. There is also the option to enter an accumulated degree day, or ADD value. Using the weather station information and the date of discovery, it returns with the number of degree days. The user also has the option of entering a TBS, or total body score, a popular method of determining PMI. Using the corrected formula we published in JFS in January 2023, GeoFOR will calculate an associated calendar date based on the TBS score and temperature data. Here's an example of the email that users receive following submission. It provides a report of the information entered along with the PMI prediction using the machine learning model. The prediction includes a predicted number of days and associated calendar date, and also an 80% prediction interval and date range. We'll provide additional information about the specifics of the model in a few slides. So far, we have collected information from over 2,600 subjects, which far exceeds any existing data set. These observations include longitudinal observations from individuals at outdoor research facilities and forensic cases, both retrospective and in the field, from several locations across the U.S. and internationally, from an ongoing and expanding network of collaborators. This unique approach has allowed us to collect an unprecedented breadth of case types that expand across environments and climate zones, deposition sites, including burials, the ground surface, and indoor cases, among others. We've also been able to examine trends between decomposition and body size, the presence or absence of clothing, skin penetrating trauma, and the effects of vertebrate and insect activity. Here's the distribution of all the GeoFOR cases and a map focused on the US that illustrates the range of variation in climate and land cover data that we've been able to capture by using geospatial technology. Although we developed the structure of this project well before the ASB standards were published in November 2022, GeoFOR is well aligned with these standards for PMI estimation. Specifically, GeoFOR uses decompositional indicators or characteristics, considers the environmental factors specific to the case, and supports estimates through scientific observations. All quantitative methods rely on representative training data sets to be able to make reliable predictions of future cases. The GeoFOR dataset allows us to use machine learning models to provide robust predictions of PMI and Bayesian models to better understand the decomposition process and inform research design in decomposition studies. I'll start by describing the machine learning model and then discuss Bayesian modeling. The machine learning model involves the steps shown here. First, the input from GeoFOR describing the condition of the remains is pre-processed, and the weather covariates are added to the data frame. The model runs and produces a prediction of log PMI plus 1, which is then converted to the scale of days. Here are some additional details about the two steps in the data preparation process. In the first step, the log of PMI plus 1 is taken for the known PMI values for training the model. This reflects our expectation of error scale for PMI, where short PMI ranges are likely to have smaller errors, and long PMI ranges will have larger errors. The plus 1 accounts for 0 PMIs, which would otherwise have an undefined log. Notice that this transformation makes the data far closer to normally distributed, which improves machine learning model performance. The second part of the data preparation is to one-hot encode the covariates. The first step is done just on the training data with known PMI, and the second step is performed on every case. The weather features used in the model are shown here. The weather covariates are gathered for 154 days prior to discovery from the National Oceanic and Atmospheric Administration. The data is queried once for each day and for each weather type, for a total of 1,232 features. To avoid overfitting the model, weather is aggregated or binned into the time windows shown here. You'll notice that the time windows increase logarithmically over time. The mean and standard deviation of each time for each feature is included in the model, resulting in 50 final weather features. We have examined a number of different machine learning models, and XGBoost has had the best model performance, with an R-squared of around 0.815. We use 10 repeats of 5-fold cross-validation method to examine the model's performance. Notice that the model performs well across a wide range of PMI values, up to around 1,000 days. Machine learning models are very good at providing predictions. However, the interpretability of the model is sometimes challenging. The XGBoost model is an ensemble of decision trees. Here's a simplified version of the model to demonstrate the intuitive relationship between decomposition characteristics and PMI. The full model combines information from 100 trees, each of which is larger and more complex than the one shown here. The tree here doesn't incorporate variables such as weather and deposition type, and is not as accurate as the current PMI estimation tool provided by GeoFOR, but it can give a sense of how the model is working in predicting PMI. To follow the decision tree pictured here, we start with exposed bone with desiccated tissue. If the characteristic is present, we next observe if weathered bone is also observed. In this case, it's not. We continue with each question until we reach an endpoint or node in the pathway shown here. In this example involving this set of decomposition characteristics, the PMI estimate would be 88 days, with an 80% prediction interval provided. Another way of looking at model interpretation is shown in this box and whisker plot. This plot shows how the model performance improves as more information is added. We start with only the decomposition characteristics and see a modest improvement by including information about insects and scavengers. There's a big increase in model performance when we include temperature and deposition type. Other weather information does not seem to improve the model performance very much. More data in the training model will allow for additional exploration of these effects and others. The machine learning models can provide powerful predictions, but the pathways through which these predictions are generated are somewhat of a black box. A Bayesian model provides a complementary approach and allows for generative thinking. By thinking generatively, I mean thinking about the process by which the data we observe is generated. In the case of the GeoFOR database, the process goes something like this. First, a person dies, then time passes and they decompose, and finally, the decomposition characteristics are observed. So in the Bayesian approach, we design a mathematical model in a way that explicitly represents this process. A starting point for designing such a model can be drawing a picture, like the one shown here, that captures our prior belief about the causal processes by which our data is generated. In this example, PMI impacts mummification through rainfall, temperature, and sun exposure. It's important to point out that this model has many unknown parameters. For instance, the model says that mummification depends on total sun exposure, but it doesn't tell us how it depends. We fit the model to find those unknown parameters. Once we've visualized the model and fit the data, then what can we do? In the forward prediction, we can say that given a certain PMI value, these are the decomposition characteristics we would expect to observe. We can apply Bayes' rule and also backward predict PMI given the decomposition characteristics observed on the body. To provide a very oversimplified example, let's think about the relationship between mummification and PMI. We'll assume that we only observe mummification, that mummification only depends on the postmortem interval, and that PMI causes mummification. We'll walk through this very simple case study to show what it's like to use this approach. We can write an equation to represent this relationship. Here, we assume that as PMI increases, it makes the probability of observing mummification either rise or fall against some baseline probability. We use our prior knowledge to inform what we think the relationship will be, and then use the data from GeoFOR to improve this initial expectation. We use the observations about PMI and mummification from the GeoFOR data, here designated as the shaded green circles. The goal is to find W0 and W1 parameters that are consistent with the observed values and the priors we placed on the parameters. Computer modeling is used to determine the best values for those parameters. Once we use known cases to determine the values of the parameters, we can look at cases that weren't part of the training sample to see if the model predicts mummification accurately. Here's a plot of the sensitivity, or how many actually mummified bodies were identified as such, and the specificity, or how many actually non-mummified bodies were identified as such. A perfect curve is shown in red and a random model as the dashed line. The results shown in blue demonstrate that we can do a pretty good job of predicting mummification. given a certain PMI value, even with this very oversimplified model. Let's take this a step forward and add additional complexity to our model to ask how body size affects our ability to predict mummification and PMI. This graph shows the results of such a model. We can see that at a given PMI value, there's a higher likelihood of observing mummification in an emaciated individual. We can use this data-driven approach to examine the effects of any covariate on different decomposition characteristics. A researcher could explicitly examine exactly when the variation arises in mummification and body size from longitudinal observations, or develop a causal hypothesis to examine the underlying mechanism for the variation. This example is one of many exciting ways to conceptualize how Bayesian generative thinking can inform our understanding of the decomposition process. With this unique approach, the possibilities for informing research design are numerous, particularly in controlled research settings. GeoFOR opens up new ways of thinking about estimating PMI. Rather than being considered an endpoint, it should be thought of as an avenue for new and innovative research to emerge using this data set. If you want to try a demonstration, here's a QR code that links to a survey demo. Thank you for your time, and we look forward to collaborating with you. And now I'm going to pass it over to Angela.
So the second part of the webinar, Improving Methods Using Machine Learning and Databases in Forensic Anthropology, explores the Forensic Anthropology Skeletal Trauma database. This research is part of an ongoing project which conducts controlled experimental bone trauma research utilizing a multidisciplinary approach through collaborations with forensic anthropologists and biomedical engineers. The research focuses on fracture mechanics to improve the validity of skeletal trauma analysis and interpretation through precise, accurate, and repeatable analytical methods. The majority of expert testimony provided by forensic anthropologists is analysis and interpretation of skeletal trauma. However, there are still major gaps between current knowledge, skeletal trauma research, and judicial standards of scientific validity. Throughout the years, there continues to be an increase in requests for skeletal trauma analysis, and we continue to see improvements in skeletal trauma analysis and methods. However, we're still lacking in links between traumatic events and fracture outcomes and established standards between analysis and interpretation. And the interpretation is what has the potential for the greatest impact and consequences. Unfortunately, at the same time, we continue to lack thorough and in-depth education and training in skeletal trauma analysis, particularly connecting traumatic events to fracture outcomes to support interpretations. So overall, we need more research to both support interpretations and to provide error rates associated with skeletal trauma. So the idea and creation of the Forensic Anthropology Skeletal Trauma, or FAST database, was built on the need for educational and training resources and to provide a resource to support trauma interpretations. So the FAST database is not simply the dissemination of the extensive amount of data from the ongoing research project. This database provides data from experimental testing parameters to fracture characteristics, from skeletal trauma with known loading parameters, to allow users exposure to experimental skeletal trauma cases for education and training and comparison to current casework. The largest obstacle for the field of forensic anthropology is exposure to trauma analysis. Few researchers get quality hands-on training with trauma cases, and even fewer have experience with cases involving unequivocally known loading and injury mechanisms. Improvement in skeletal trauma analyses and interpretations is dependent upon dissemination in a user-friendly format that allows for training and education and supports forensic professionals in practice. Currently, all FAST data are from a single NIJ project, which consists of 100 human tibiae dynamically impacted at midshaft in a 4-point bending testing scenario, as demonstrated in this video. The project includes 6 test series, tibiae impacted at 6 meters per second in lateral, medial, and posterior anterior directions, tibiae impacted at 2 meters per second in lateral, medial, and posterior anterior directions, tibiae impacted at 6 meters per second in a lateral medial direction with an axial preload, and legs impacted in a lateral medial direction at 6 meters per second. The FAST database consists of experimental research only, and a common question we get is why not include forensic cases? So our goal in developing FAST is to provide a resource that utilizes skeletal trauma from known loading conditions. And this level of detail is not possible in forensic cases. With experimental cases, we know the exact loading conditions, the mechanism, the rate, the position. We collect data about the bony response throughout the duration of the event, as well as known fracture data, such as initiation and propagation data, and of course, the results of the fracture analysis. So the FAST data includes subject level data, so information about the individual, such as age, sex, and stature. Experimental testing data, the mechanism of trauma, so blunt force or sharp force, the loading direction, whether that's lateral medial, posterior anterior, and the loading rate. We also have injury data. So we utilize the abbreviated injury scale score. And so those data are calculated and included in the records as AIS, or the maximum AIS, which allows for direct comparison to clinical data. Element level data, so the element, the side, and standard measurements recorded prior to testing. We provide the associated project with the specimen. Biomechanical data, such as output force, percent displacement, stiffness, and energy. And fracture data. The fracture data variables are based on the AO-OTA fracture and dislocation classification system, with additional variables of interest that may be of interest for forensic anthropologists. So which include the broad classification as a complete or incomplete fracture, the type of fractures, so for example, simple or wedge, the fracture group, examples are transverse, oblique, or intact wedge, the broad location relevant to that specific element, so for example, proximal, shaft, or distal, and a specific location, which is the measurement of the center of the fracture provided as a percentage of the length of the bone. The FAST database is accessed through the Injury Biomechanics Research Center website, so ibrc.osu.edu. And FAST has its own tab within the website. The next couple of slides will demonstrate how to request access to FAST, how to access the database, exploring the records in FAST, and finally, how to run a query in FAST. So to access the database and request user agreement, you go to ibrc.osu.edu, and then you'll go ahead and click on the FAST tab. Once you're there, you can scroll down, and then you'll click on the click here to request access to the FAST database. This brings up the FAST database access request form, which you'll fill out with your first name, your last name, your title, whether that's undergraduate student, graduate student, professor, practitioner, your affiliation, whether that's a school or place of employment, your reason for access request. So if it's for research, if it's for case comparison or education or training, and then your email. Once all of this is submitted, at the end, this will go through our IT department. If any of these fields are left blank, that form won't get forwarded on to me for approval. So I need to make sure that all sections are completed. Once you click next, you'll get to our data use agreement. So you can go ahead and read through all of these. And at the bottom, you'll be asked to add your signature. This verifies that you have read the data use agreement and agree with all of the terms within the agreement. Again, once you're done with your signature, you'll go ahead and save signature and click submit, and this will be transmitted to our IT department, which will do initial review of all of the requests. You'll get a notification that your request has been submitted, and that shortly you'll receive an email about the results of your request. So once your request has been approved, you'll get an email that says REDCap access granted, so be on the lookout. It won't say FAST, it will say REDCap. And within that email, I'm going to ask you to click on the link to set your password. So you'll go ahead and set your password, and this will be your password to access FAST via the REDCap link. Once you click submit, your password is all set and you're ready to access the database. So you can access FAST through the link provided in a separate access granted email. So you'll go in, you'll log in with your username and password, and then at the top of the screen, you'll see a My Projects tab. You can click on that, and then you'll scroll down and click on the FAST database. This will bring up our homepage, which has some information about FAST. And then if you go to the Data Exports, Reports, and Stats link, you can click on the View Report of all data. This provides you a list of all the records included within FAST, and you can go through and look at all the data in this this table, or you can click on each individual record ID, and that will bring up additional information and views. If you'd like to run a query in FAST, you can do that as well. And you can also access FAST through the IBRC website. So you'll go to IBRC, you'll click on the FAST tab, and then scroll down to the click here to access the FAST database in case you lose that initial request granted email. You'll go ahead and enter your username and password and log in. And it's the same as the other way to access it. You'll go ahead at the top and click on My Projects, and then you'll click on the FAST database link. So again, we're at the initial homepage, and we can go ahead again and click on the Data Exports, Reports, and Stats link. So instead of clicking on the All Data View Report, we're going to create a new report. For all new reports, we need a title or a name of the report. So ours is Example Report for this demonstration. We're going to leave the user access alone, and we're going to go on to step 2, which is fields to include in the report. So this part of the query allows you to select all of the variables that are relevant for your query. So we went ahead and selected sex, and you can scroll through. This lists all of the variables available for you to select. And we'll click to be assigned. And for our last variable, we'll go ahead and select age of the individual. Step 3 involves filters. So if you want to filter for something specific, for perhaps your research or your case comparison, you can do that here. So for our first filter, we'll select sex, and we're only looking for female specimen. And then for our second filter, we'll go ahead and select tibia side. And with this, we only want to look at left tibia. We can then scroll down to the bottom and click Save Report. And then we'll go ahead and click View Report. So this brings up your report. So the total number of results returned was 12 out of 60 records. And here's the list of those records. You can select individual records to then scroll through all the data for each record. So we can scroll down and we'll see we have our subject level data, our experimental testing data, injury data, element level data, the project, the biomechanical data, and the fracture data. And then below that, we have our imaging data. So we have pre-test x-rays in both the anterior, posterior, and lateral medial directions, as well as our post-test x-rays in those same directions. We can then scroll back to our report just by simply clicking the back arrow. And we could do this for all of the individual records within our queried report. So what's the current state of FAST? So right now we have over 100 users worldwide. And the most commonly requested reasons for access to FAST are for education and training, casework comparison, and research. So we are reaching people are requesting access, but what's the future of FAST and where do we go from here? So as I stated before, FAST currently only consists of a single element, the tibia, and we obviously want to expand and include additional elements. So our plan is to incorporate elements that have either previously been tested within our lab or will be tested in the near future. And this includes ulna, radii, and individual ribs. We also plan to incorporate 3D models. These models are built from post-test CT scans and then reconstructed. The goal is to have them included within each record and that the user can manipulate the model to look at whatever area or feature of interest they would like to see. Additionally, we'll include fracture surface images for those interested in looking at some fractography methods, and we'll include highlight traits that we see within each sample. Additionally, beyond just single elements, we will include whole body experimental cases, and these are experimental cases in which a whole body has experienced some traumatic loading event. And those will be as a separate portion of FAST where you would search for a whole body test. We also plan to incorporate advanced statistical output for people to access both frequencies, predictions, and things like that to help them to assist in their interpretations. And we're always looking for user input. So if there's things that you would like to see in FAST that aren't there currently or aren't listed in the future of FAST, let us know. If you're having issues with anything, again, let us know. When you click that Contact FAST Administrator button, that will send an email directly to me so that I can address your comments or questions. So I'd like to thank the anatomical donors of The Ohio State University, without whom this research would not be possible, and the National Institute of Justice for funding this research. I'd also like to thank the PI and all the co-investigators, as well as all the faculty, staff, and students, specifically Dominic Beltry for putting all these videos together for me, and everyone in the Injury Biomechanics Research Center for all their contributions and support. So thank you for joining our webinar, Improving Methods Using Machine Learning and Databases in Forensic Anthropology.
Hello, everyone. I am John Grassel, a Forensic Science Program Manager at RTI International. Thank you, Katie and Angela, for providing these very interesting presentations. And also, I want to thank Carl Earhart for also joining us today. Carl is also with the GeoFOR project. We have several questions from the audience. And again, if any audience members have additional questions, please type them into the chat. Our first question is involving GeoFOR, and it is, what are the safeguards in the software when training machine learning from potentially sensitive, confidential data?
Yeah, thank you for having us. Nice to be here today. So a couple perspectives. So yeah, I was really concerned about that and thinking about the GeoFOR data set. And so we tried to design the survey to be as anonymized as possible. So it's very generic, broad categories. So whether the individual is an adult or an infant, different investigators or people inputting data, you can input the exact location of discovery or a nearby general location. So in those ways, we've tried to safeguard against any confidential materials. And then as we're training the model, maybe Carl can speak to that part.
Yeah, so the model training only involves the model getting to look at the decomposition state, as well as insect and scavenger activity and weather. So the only thing that something like location data, which is potentially personally identifiable, is used for is to get that weather data. But before the weather data comes to the model, it's highly processed and aggregated up so that it's no longer possible to trace it back to any particular location. So by the time the data gets to the model, there's really no personally identifiable information left.
Thank you so much. Our next question, Angela, this is for you, involving FAST. Why did the FAST database start with the tibia? What was the reasoning behind that? And aren't there more relevant skeletal elements to forensic casework?
Yes, we get that a lot. Like, what about the cranium or what about the hyoid? And I hear you, I do. And we are exploring additional funding opportunities to expand to testing on additional elements. We chose the tibia for a couple of reasons. One, to explore whether our current understanding of long bone fractures is accurate. When there's bending, do we see that typical or expected wedge fracture? But also for applications beyond forensic anthropology, pedestrians versus motor vehicle accidents or crashes, the tibia is one of the most common elements fractured. And so it's applicable across different scientific fields.
Excellent. Yeah, that's, now that you mention that, of course, the automobile accidents would be extremely common use for that. Thank you. Carl and Katie, could you tell us, will or do the data parameters include remains that have been recovered from water?
Mm-hmm. That is something you can select in the deposition code, and we do have data in the data set from water recoveries that people have entered in the data, so that the model does predict from water, although that's a small component of the cases, and so the more training data you have available, the more accurate the results will be. We hope to increase those variables over time as the data set grows.
Great, thank you. Angela, back to you. Don't students get skeletal trauma training in forensic anthropology programs? And why do you feel that there is a need for such a database as an educational tool?
Yeah, so to some degree, students get training. It's just dependent upon the program. So skeletal trauma analysis and interpretation might be part of their coursework, or they might get hands-on training with forensic casework with their advisor. But the critical part, or the important part here, is that what's lacking is training on skeletal trauma from known loading conditions. So every element in FAST, we know exactly the exact position that it was in when it was impacted. We know the force, we know all the information about the individual to help with that, learning how to interpret these fractures.
Thank you. Katie, Carl, back to you now. Does GeoFOR work best, meaning better PMI, for certain lengths of time? For example, it looks like the model amalgamates data for the first 3 days. Would it not be possible then to determine a PMI for, say, less than 3 days?
Mm-hmm. Do you want to handle this, Carl?
So I would say that in general, we observe that the model behaves best for the kinds of cases that are most represented in our training data. And where the model actually performs worst is with really high PMI cases. And that is because those cases are just underrepresented in our training data so far, with in comparison with more mid-range PMIs. So that's, again, as with water cases, as more data is added to the GeoFOR database and is used to train the model, we expect to see hopefully ever improving predictions for those cases.
Thank you. Angela, will the current version of FAST continue to grow while planning for the next updated version?
Yes, I have 41 more records of tibiae to put in, which will be done pretty soon. And then we'll start inputting records for ribs, and we'll just start working through previous experimental research that we've done in the Injury Biomechanics Research Center while we're exploring updating.
Thank you. Carl and Katie, this question is, how do you account for scavengers in the model? In your presentation, you mentioned that you use donated bodies in the models, but the bodies often decompose with scavengers are intentionally excluded. Do you account for this exclusion since the viewer says we know that scavengers can accelerate the decay of bodies?
Yeah, that's a great question. So about 750 cases are from research facilities, and so those generally have limited scavenger availability from them. And the other 1,850 cases are from medical legal investigations, and so they have a wide range of different scavengers associated with the bodies. So we do have that as a component that the model looks at and takes into account as it's making its predictions. There are various scavenger categories, so from rodents, vultures, and carnivores, and so those different patterns and animals are going to impact the model in different ways.
That's great. Well, there's a break in the questions. Katie, Angela, Carl, do you have any final thoughts you'd like to share with the audience? Something that may not have been covered with the question?
Yeah, I could just say that so as we've collected the data at various, working with different coroner's offices and medical examiners' offices, I think that it's been useful both to have a method of making a prediction. I think most of the time we're stuck with just based on your experience and your best guess. This is generally what I think the time frame would be. So this at least gives us a place to start from a data-driven perspective. But it's also been really helpful for these offices that are using interns and students that are interested in forensic science. Allows them to look at retrospective cases and to think about decomposition in a way that really focuses their attention on the variables that are important. So I think that the aspect of it as a learning tool has been really useful too. And people have commented on that as a way of sort of getting students into a meaningful research project in forensic sciences. Another thing that we've talked about, yeah.
Has GeoFOR been used in forensic cases to date?
Yep, yeah, several offices are using it, and to make, at least to give you a place to enter into the conversation. Really the methods that we have available are pretty limited from a data-driven perspective, and so this is accessible to people, it's free, and so it can be a useful method that several offices have found and put to use in their cases.
Great. And Angela, I know that you mentioned that in your presentation about requesting access to the FAST database, and Katie, you mentioned requesting a demo of GeoFOR. Are both of those options still available to users?
Yes, FAST is always available to request access to, and I am constantly checking my emails, so those get approved pretty quickly, and it's free for any user.
Yeah, and users can, it's the same with the GeoFOR website. We have a place where you can look at a demo if you're not sure what would be required, and then also on that same website where you can request access and become a collaborator.
Great, thank you. Katie, how does the GeoFOR PMI correlate with other methods for estimating PMI, such as microbial clocks, insect evidence, etc.?
So as far as I know, there's very little specific ways that you can determine a PMI interval. So I would say it's longer. It covers a wider range of time periods. It requires less expertise, so you can get a quicker answer to start your investigation. And yeah, so we've looked at it in comparison, well, a little bit to total body score, at least comparing the methods that are available. And this method does very well based on the large data set that's available. It seems to be fairly applicable across a variety of different settings and time periods. So.
Great. And just a follow-up question to that refers to the accuracy rate. One of the users wants to know, what is the accuracy rate of GeoFOR, and have you started validation studies yet?
Yeah. Do you want to take the accuracy and validation studies that are available?
Yeah, so we've validated our model using repeated k-fold cross-validation and find that it has a generalization capability of an R-squared of about 0.82 on unseen data, so data that's not in its training set. Yeah, that's something that's achievable through the size of the data that we're working with. If we have access to a smaller data set, we don't see that level of performance, and it's only when we make use of the full size of the GeoFOR data that we're able to get that level of performance.
Thank you very much. If there are no further questions, we are going to wrap up today's webinar. Katie, Angela, Carl, I thank you so much for your time and presentations. Very informative. You can tell by a lot of great questions from the audience that we've had today. So thank you so much. Please, everyone, feel free to reach out to the presenters if there are additional questions. I know oftentimes those questions may come a little bit after our presentation. Thank you again.
Thank you, John.
Thank you.
Thank you.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.